Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into real-time analytics, the system that turns millions of streaming events into live dashboards, metrics, and alerts. We'll cover the end-to-end architecture using Kafka, Flink, ClickHouse, Redis, and modern dashboard serving techniques. Whether you're preparing for a senior engineering interview or building real-time analytics infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into real-time analytics, the system that ingests millions of events per second, processes them continuously, and serves dashboards and alerts with sub-second latency. If you have ever wondered how platforms like Uber, LinkedIn, Netflix, or modern ad tech stacks track live users, detect fraud, monitor campaigns, and optimize operations in real time, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FAANG interview or building event-driven analytics infrastructure, let's get into it. Here is the core problem. A modern product can generate millions of events every second. Clicks, impressions, API calls, transactions, IoT sensor readings, application logs, and delivery tracking updates. Business teams need to see trends, detect anomalies, and take action immediately. But traditional data warehouses are built for batch. They ingest data every hour or every day, run heavy transformations overnight, and produce dashboards that are stale by the time they are opened. By the time a batch report shows a traffic spike, a payment failure, or a fraudulent campaign, the opportunity to react has already passed. The business needs a real-time analytics system that continuously ingests, processes, stores, and queries event streams so that decisions are based on data that is seconds old, not hours old. Let's walk through the functional requirements. First, the system must ingest high-volume event streams from many sources: web and mobile clients, back-end services, APIs, IoT devices, and logs. Second, it must validate, parse, and normalize events against a schema registry, attaching metadata and dimensions such as user, region, device, and campaign. Third, it must compute real-time aggregations over sliding or tumbling windows, including counts, sums, unique counts, top K, percentiles, and rate metrics. Fourth, it must serve interactive dashboards and alerts, supporting filtering, drill down, and time series queries across many dimensions. Fifth, it must support ad hoc analytics, retention policies, and the ability to backfill or reprocess data when schemas or business logic change. These 5 capabilities turn raw events into actionable, real-time insight. Now the non-functional requirements. End-to-end latency must be low. From the moment an event is produced to the moment it appears in a dashboard or alert should be on the order of seconds, not minutes. The system must support high throughput, potentially millions of events per second, and scale horizontally by adding more partitions and workers. It must be fault-tolerant. A node or job failure should not lose data or corrupt aggregates. Query latency must be sub-second for interactive dashboards, even when data volume is huge. The system must be highly available because operational decisions, fraud detection, and revenue optimization run around the clock. It must remain cost-efficient by separating hot and cold storage paths and using approximate algorithms where exact precision is not required. And it must handle late and out-of-order events correctly. Here is the high-level system architecture. On the left, event producers such as web clients, mobile apps, back-end services, IoT devices, and log shippers emit events. These events pass through a load balancer and API gateway into a Kafka ingestion layer, which provides durable, high-throughput buffering and decouples producers from processors. A Flink stream processing cluster reads from Kafka, validates schemas, enriches events, assigns windows, and computes aggregations. The aggregated results are written into ClickHouse, a columnar analytics database optimized for fast time series queries and high ingestion rates. Redis sits in front of ClickHouse as a hot cache for the most recent dashboards and pre-computed metric cards. A dashboard and API layer serves the user interface, while a separate alerting service evaluates thresholds and triggers notifications. Older data is archived to object storage for batch backfill and long-term analytics. The key metrics to memorize: cold. Event throughput, measured in events per second, tells you how much volume the pipeline can handle. End-to-end latency, from event production to dashboard visibility, is the core promise of real-time analytics. Query latency at the P95 and P99 tells you whether dashboards feel interactive. Data freshness measures how far behind the latest event the dashboard is. Cardinality, the number of unique users, devices, or sessions, drives the cost and complexity of exact unique counts. Error rate and data quality score measure how many events are dropped, malformed, or duplicated. Cache hit ratio shows how effective Redis is at reducing load on ClickHouse. And availability is critical because the business depends on live data. These metrics are what interviewers and operators actually care about. Let's trace the end-to-end user journey. A product manager at a ride-sharing company opens the real-time analytics dashboard during a major concert surge. She sees active users, ride requests, driver availability, and estimated pickup times updating every few seconds. A region shows a spike in ride requests but a drop in match rate. She drills down by city and device type and sees that the issue is concentrated on older Android devices. Meanwhile, an anomaly detection alert fires for a sudden increase in failed payment events. The operations team receives the alert, investigates the associated traces, and rolls back a recent configuration change. The product manager also uses a live campaign dashboard to shift marketing spend toward the surging region. Within minutes, decisions are made using data that is fresh, not stale. The core models and algorithms. The event schema defines the structure of incoming events, including required fields, optional dimensions, and version types. Windowing is how stream processors slice unbounded event streams into bounded chunks. Tumbling windows are fixed size, hopping windows overlap, and session windows are defined by user activity gaps. Aggregation functions compute counts, sums, unique counts, percentiles, and top K over each window. Materialized views in ClickHouse precompute common queries, so that dashboards load instantly. The state store in Flink holds intermediate results for windowed and keyed aggregations, and must be queryable and checkpoint. Time semantics are crucial. Event time is when the event actually occurred. Processing time is when the system observes it, and watermarks are the mechanism for handling late and out-of-order data. The key trade-off is latency versus accuracy. Exact counts on high cardinality are expensive, so approximate algorithms like hyperloglog and countmin sketch are often used. Now the low-level design deep dive. Kafka topics are partitioned by event type and region, and a schema registry enforces compatibility. Flink jobs consume from Kafka, deserialize events, perform enrichment and validation, assign windows, and compute aggregates. Checkpointing and save points provide fault tolerance and exactly once semantics. Flink writes results into ClickHouse using idempotent inserts, typically partitioned by time. ClickHouse uses merge tree engines and materialized views to maintain real-time rollups. Redis stores hot dashboard tiles, recent metric cards, and alert states so that the most common queries never hit the database. The dashboard API routes reads to Redis for the hot path and to ClickHouse for historical drill downs. The alerting service pulls metric values or consumes a dedicated alert stream, evaluates threshold rules, and routes notifications. For late arriving data, Flink watermarks and a periodic batch reconciliation job ensure correctness without blocking the hot path. Key takeaways for your interview. First, real-time analytics is not just a streaming engine. It is a three-layer problem of ingestion, stream processing, and fast-serving storage. Second, always discuss event time, processing time, and watermarks, because handling late and out-of-order data is what separates toy systems from production ones. Third, know when to use approximate algorithms like hyperloglog for unique counts and countmin sketch for frequency queries when exact answers are too expensive. Fourth, separate the hot path served by Redis from the cold path served by ClickHouse to balance latency and cost. Fifth, plan for backfill, reprocessing, and schema evolution because business logic changes and late data are inevitable. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for real-time analytics. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on real-time analytics. We covered the full picture, from event ingestion and stream processing, through ClickHouse serving, Redis caching, alerting, and the low-level design of the Flink DAG. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.